Welcome to this video. I'm going to try to prove for you the product rule in calculus. So at some point, hopefully in grade 12, when you're taking calculus, your teachers are going to be showing you this, and if they don't, I think it's a mistake. I think it's worthwhile to understand where the product rule comes from. So what is this product rule all about? It is when you have a function, so I have designated that function's function h of x, and that function is made up of the product, so the multiplication of two separate functions. And this product, what we would want to be able to do is we would want to be able to find out what the derivative is, so how to differentiate h of x if it is made up of two particular functions just multiplying each other. Now, we do have to make an assumption here, and my assumption is going to be that the derivative of the first function, so the derivative of f, and the derivative of the second function, so the one that is multiplying, of g, they both exist. So what that simply means is that the functions f and g are differentiable functions. So they're well behaved enough that we can take the derivatives of those functions. So now, what does the product rule tell us? Well, the product rule tells us that if you wanted to take the derivative of h of x right here, then all it would be is kind of a addition or a summation of two products. And it's interesting. So it's not very difficult to memorize this product rule. So all it says is, so as you can see here, if you take the first function, f, you're going to differentiate it, and you're going to multiply it by the second function. That's going to be your first term. Notice you're multiplying it by just the function and not by its derivative. And then you're going to add, so it's almost like splitting it into two. Okay, so here you're going to be freezing, so you're going to be taking the function f, not doing anything to it, and then simply just multiplying the second function. So that's what we want to be able to prove. Okay, so let's try to make that happen. If you're going back on this and you're trying to show this proof, so this is how you can go about. Now go back to the original definition, okay, of the derivative, which is with respect to the limit as h is approaching to 0. And what we're going to be doing is we're going to be taking our function, so this would have been h, and then x plus h minus hx, and this is of course all over h, and that is the derivative definition. So that's what we want to be able to do. Now h itself is of course the product of this f and g, so I'm going to just do the substitution. So I'm going to just first substitute into this. So what I'm going to have is I'm going to drop this limit for a moment just so that I have enough space here to kind of do things around here. So for this, when I substitute, I'm going to get f, x plus h multiplied by g, x plus h. So that's the first thing. Now I'm going to subtract the h, which is just simply the multiplication of the two functions. So that's f and g. My h in the denominator is going to stay there. I'm going to drop it for just a moment in this proof because I just want to concentrate on the numerator. Now, as it stands here, it's not very obvious that this is exactly what we're going to be getting. So how do we get here? Well, it is actually one of the tricks that we're going to be using. So the trick is that, let me just rewrite, okay, so this right here, so as it is. So I'm going to take this, I'm going to copy it down or duplicate it, okay, I'm going to put it here on the left, all the way on the left. I'm going to take the second one, so here, this entire thing, right here, I'm going to duplicate and put it all the way here on the right, because I'm going to be adding, okay, and subtracting a particular term. So this is minus. Now at this point, what I'm going to do is I'm going to add and subtract a couple of terms. So I'm going to add the following. So I'm going to say f, x, multiplied by g, x plus h. So that's going to be my first term. And then I'm going to subtract Okay, so within here, I'm running out of space, so I'll put it right underneath it, and I'm going to subtract that particular term. So I'm adding and subtracting this term. Now you might say, well, if you add it and subtract it, it equals to 0. Exactly, that's the point of the proof, because we do not want to change this overall numerator. So by us adding and subtracting right here, we're not really changing the numerator at all. And now I'm going to be massaging this out. So if you notice, what I have is I have in these two terms, so this one right here, and then this one right here. So I'm going to group those two terms together and then factor out the g of x plus h. So what's going to happen is the following. I'm going to get f x plus h minus fx, and all of this, okay, and I'm factoring out this g out of here because it's common to both, so it's going to get g x plus h. So I hope that you can see that within those two particular terms, this one and this one. So that's what I have done, and that is my subtraction right there. Now in the next one, so what I'm going to do is I'm going to group these two terms together, and notice that what these two terms together have now in common is the fx, okay? So this is right there. So what I'm going to do is I'm going to take that fx out. So I took it from the first one, and then I'm going to also take it from the second one out, and all I'm going to have left is g x plus h, so that's right here, minus, so that's the minus, g at x, okay? And this is what I have. Now, this is my numerator, please remember. So if I'm going to just center it around here, this is what I have within there. Now, this entire thing, of course, was all over h, and we had to take the limit as h is approaching to 0. So now we're very close, and I hope that you can see this. Now, I'm going to break this down into two things because I have this addition. So if I do that, then I'm going to have this right here. So I'm going to just duplicate it. Okay, so I'm going to have it on my own right there. I will write it over h. So that's that. Plus, okay, so that's my plus coming over here. And then I'm going to take this term in the numerator. So duplicate it, bring it back over here. And then set it all over h as well. So all I have done is I've just split that h over. I'm just basically creating two fractions in here. Now, from there, what I have is I'm going to group, okay, so this right here on its own. So this h is going to bring into here. That g is just multiplying. So really, so now I'm going to start kind of rewriting this. It's going to be x plus h minus fx. This is all over. Okay, I'm going to keep that h over there, and then this is multiplying g x plus h. Then I'm going to have plus, then I have my second one, so this is going to be the fx, okay? Then that is going to be multiplying. Now the other, so g x plus h minus gx, and this is going to be all over h. Okay, so we're getting very close. Now, let's not forget that this entire thing, so this whole thing, was with respect to a limit. So we had to take the limit as h is approaching to 0. Well, now we can use our limit properties within here, okay? And what we will have is, so let me just concentrate first on this right there, and then what will that equal? Well, this is going to be limit as h is approaching to 0. Okay, so I'm going to take this whole thing, okay, duplicate it, so bring it down here. So that's the limit of that. I'm going to try to squeeze this down just so that it doesn't take as much space. Multiplied by the limit. So I'm bringing this limit into this, and I'm bringing this limit into that. So that comes in from limit properties. And within here, so that's going to be, so now I can take this, I'm going to duplicate it, okay, bring it back, okay? And that is that first term. So I have just concentrated just on this. And now I'm going to bring that limit over the sum and do it also to the second term that you see there. So into this term right there. Now, before I do that, notice what happens. This right here, this is just the definition of the derivative of f. And now this, as the limit tends towards 0, because our g is a differentiable function, so this h, as we have it within our function, okay, as h tends towards 0, this really just becomes g at x, because h tends towards 0. And if you now think about it, this is exactly, so if I scroll back up here, this is exactly what we were after. This multiplied by g. And now you would do exactly the same thing with the second. So what we would get is, I'm going to just switch. So I'm going to have a limit as h tends towards 0 of fx, which really is just a constant with respect, because we're letting h tend towards 0, so nothing really happens there. There is no h, multiplied by the limit as h tends towards 0 of this entire thing right there. So I'm going to duplicate it, okay, and bring it back over here. And now I hope that you notice, well, there is no h there. This is just simply fx. And now it is multiplying. This is nothing else but the derivative of g. And that, now, because we're adding these two things together, right there, is actually the entire proof. So you have your product rule set. So the only really idea behind this product rule was the fact that we had to add and subtract these two terms. And so that's a little bit of a trick. And as you do more and more proofs, you will realize that sometimes you can do these proofs, okay, especially if you want to be separating things kind of term-wise from each other. So that is it. That is the proof with respect to calculus for the product rule. All right, so I hope this is helpful, and we'll see you in a future video. Bye, everybody.